topic of my presentation today is passage-based answer set graph approach for query performance prediction. My name is Ghulam Sarwar, and I am a PhD student currently at here in Galway in National University of Ireland. So the area of my research is mainly falls under the information retrieval. Information retrieval deals with organization, storage, retrieval, and the evaluation of the information of documents, particularly the textual information. There's different retrieval models that can be used to index and retrieve the information. And like one of the examples are vector space model or probabilistic models, Boolean models, etc., are the ones that are common approaches that have been used in the past. So there's some of the problems that are really common in generally in information retrieval is that due to the nature of the documents written in a natural language way, it's a difficult problem to find. It's a challenging problem to find a document that answers users ask in particular, like especially, for example, when we are trying to evaluate the performance of the retrieved results and seeing that whether how much they are relevant to the given query. In IR, when we don't have the relevance judgment finding a way to distinguish between an easy query and a difficult query is a challenging task. Here, when I use the word easy query, means that the return documents for a query are on point in answering the information, and vice versa for a hard query. Query difficulty may vary among queries and may even vary for the same query as well. Like for there are issues like vocabulary mismatching, then there's some topics that are even hard to answer as well. And even when we train certain systems in certain in topics, they might be some particularly domain specific, and yet they may give a better performance for in some scenarios, but in general they may not give the performance that they are giving. So what we are looking for here in query performance prediction is the main motivation is to evaluate the retrieval performance in the absence of the relevance judgment information. So there's two ways of doing that. So one is the pre-retrieval prediction, and the other is the post-retrieval prediction models. So pre-retrieval is that can the query provide related information over the given data sets. Like for example, if my query is that in which country ADCS conference held, so if I have any documents that are related with Australia and the conference, the ADCS, is my query, does the data set have something relevant to that? So pre-retrieval models covers that kind of tasks. Post-retrieval, on the other hand, checks that in the return list given to a query, what chances are there that an answer set contains the relevant information. So there's several, so the main thing is here is that the main purpose of all the QPP indicators is to differentiate and formulate strategies to improve the performance of an IR system with the gain knowledge of a given query. The approach we present in this presentation falls under the post-retrieval models, and to check the effectiveness generally for a predictor, usually a correlation between an average precision is used against the result or the number that comes against the predictor. We are using basically a passage-based approach. So just a small overview of passage level retrieval as well. Here is usually considering the documents as as passages are considered as the pseudo documents or part of a chunk of a document. There are many ways to distinguish between how do you want to specify the boundary of a passage. Previously in the past, people have used discourse, semantic passages, overlapping window size approaches, so on and so forth. In some situations considered paragraph as a boundary as well. But generally the idea is that you stored passages and index them, and then can send a query and retrieve those passages back as well. In normal ad hoc passage retrieval system, when you send a query, you retrieve the responses back, and then you put them in a document, convert them into a document level approach, and then apply certain approaches like max passage approach, sum of passages, and so on and so forth to re-rank what best document that you can retrieve. So this is general overview of the passage level retrieval that we do for to identify the ranking of the documents. what we are doing is the answer set passages. So let's say you send a query, and before you send a query, we have different type of test collections. We parse the documents and you put them into an IR system. The approach that we are using is the overlapping window size approach, which is commonly used in the past as well, for as a to differentiate between the passages from one another. And then when you send the query, you retrieve the responses back, and then we generate an answer set graph out of it. And then the graph, when I meant is generated, is like, for example, if we take this diagram as an example, so we have 5 passages returned for a given query. So we generate a complete graph, and where nodes represent the passages and the edge represent the cosine similarity, or a similarity, just call it for now, is between those passages. We use at the moment the cosine similarity, and we generate a complete graph out of it. Our approach is based on basically a cluster hypothesis, which states that the similar documents within a cluster represent the same relevance of the information need. So when we have the overall complete graph, then we try to truncate some edges from the graph by using an edge count. So say we want to take the top 5 edges, and then we truncate all the other edges based on the edge weight, and we take only the top 4 or top 5 or top 10 edges, and we use that graph to apply different graph properties on top of it and see can that be used as a predictor for the query performance. Some research questions that we are trying to answer here is that could combining the relationship between passages of the answer set can be an effective measure to predict the query performance. Another one is that once we have what different are there any particular graph properties that can be used to measure and to evaluate the query performance. Like I said, that our approach is based on the cluster hypothesis. So in generally, what happens is, so we hypothesize that by considering the cluster hypothesis, we would see a significant difference in passage answers to graph against easy and difficult query. And again, the reason for that is that for easy queries, you might find large clusters of the related topic with high similarities, but they'll be closer to each other. However, in the case of a hard query, you might find that these clusters are all over the place, and they may have similarities with each other, but small cluster, but overall they are showing topic drifts from each other. So we want to see that can we capture that kind of information in a graph and use that. And another thing that we are checking is how well connected these answer sets graphs are. So can the different features can be used to determine the quality of the graph, and can that be used as an effective measure for QPP tasks? So there's two different graph measures that we have introduced here. Is one is the cohesion. So basically, in cohesion, what we are doing is that we define document cohesion based on how well passages are connected with each other within the answer set. So for example, if the return set of a passage, let's say, discussed a similar topic, then the cohesion of the answer set will be higher. And as per the cluster hypothesis, like I mentioned, the nodes, the idea is here is that the nodes that belongs to the same cluster convey similar relevance to the information need. So for an easy query, as the return documents will largely be relevant, therefore, according to the cluster hypothesis, these documents will be similar to each other. Therefore, the cohesion score can be higher or different from compared to the one which is a hard query, and then can be used as a measure to distinguish between an easy and hard query, and hence as used as a measure for QPP. Another one that we used is the minimum spanning tree. So minimum spanning tree is used previously for in different network graph information related work as well. So here the idea is that the resulting graph that you get is the connected graph, but involves all the original nodes. MST illustrates the overall connectedness of a graph, and by taking the lower score edge to generate MST, what we are doing is that we are overall trying to capture the connectedness of the graph within the response. And here again, the idea is that for easy query, we could expect large clusters of related topics with high similarity. If that's the case, then for example, if we're taking the minimum spanning tree, then even the nodes with relatively a lower similarity score in the graph would have a higher edge because they are strongly connected with each other compared to the graph that is formed for a hard query. So that's another motivation behind using the MST approach. So this is just an example of the same graph that I've shown before. So 5 different nodes that are connected with each other. Taking an edge count of 5, we get a cohesion score of 0.45. And for the same graph, we get a cohesion MST score of 3.4, 3.65, just to show how they are calculated for each graph. The experimental setup that we used different types of test collections, Cranfield, WebAP, and Ohsumed. This is the initial work of our, and we took these 3 different types of test collection because I think one is really small. WebAP is relatively larger in terms of the text, but Ohsumed, for example, have very abstract, very small text documents, abstracts, but there's large amount of documents compared to WebAP and Cranfield. So they're different in characteristics, and we used as a start to compare these 3 test collections and retrieve the results and see how they're performing. So this is just we used Apache Solr to index our documents, which is based on Lucene. And then we retrieve the responses, send the query to Apache Solr. We retrieve the responses, which is the passages, for example, and then we built a graph out of it. Then there are other query performance predictor as well that we used as baseline to compare our results. So standard deviation, for example, is one which can be used to quantify the variation of the similarity for a given query in the rank list. Standard deviation is one approach, and we use the standard deviation of top 100 passages and top 100 documents to measure the standard deviation. Then there's 2 other very commonly used approaches is the WIG and NQC, where NQC utilizes similar approach as standard deviation by further normalizing it with the overall corpus score. And the motivation in NQC is to estimate the query drift. However, similarly, the WIG measures the difference between the average score of the top ranked documents and of the corpus. So these are the 3 main baselines that we used, and we used the document levels as well. So say for the same query, we sent we got the results back for top 100 documents, so on and so forth, and we did the same for passages as well, so we can compare both against our own approach. So one thing that I've mentioned here is that the edge count. So when we generated our overall answer set complete graph, so we use different edge count. So taking only top 100 edges, top 250, top 500, top 1000, and so on and so forth. And we have seen that the best results that we received is by using the top 250. And the idea is that when we increase more edges, we're somehow increasing the noise as well. And by having too low number of edges, we saw that, like for example, for 100, the results were not as good as for 250. So we found 250 as the best edge count for our results for the cohesion and MST. And we use Pearson's correlation again to measure the performance as a predictor between the average precision and the results that are coming from the different QPP approaches. Similarly, and here is the table for all the results that we have seen. So as you can see here, the first 3 ones are the standard QPP approaches that are previously been used. The other 3 are the NQC, WIG, and these are all at the passage level. And then we compared them with the cohesion and the MST approach. We can even see that for big size big document size collection, like for example WebAP, we saw that even the passage ones, they gave a positive correlation compare and all of them shows the positive correlation even for the passages one that are NQC and WIG. And the MST approach for us has given the best result for Cranfield and the Ohsumed. And for Web AP, we did not see that the best correlation. And I think one of the reason that we have noticed is the way the Web AP is designed. So for MST, when you retrieve the responses back for a given query for a Web AP, the average precision is so high and the documents are very tightly clustered with each other. So when we use the truncation method to remove some of those edges and apply the MST on top of that, the overall, I think there is a chance that the overall there's some effective edges or the nodes that can be that can have been truncated out of it as well. So that could have been one limitation about the MST, but our next work is to apply the same for other type of test collections. So this leads to the conclusion in future work. So our MST approach outperforms the existing QPP approaches against the Cranfield and the Ohsumed test collection. We've seen that the MST approach also outperforms the WIG and NQC approach for the Web AP test collection as well. Then for large size test collection like Web AP, passage-based approaches, like I mentioned before, perform better than the document-based approaches. Our next step is to do the same work with different large size test collection like GOV2, Acquaint, MS Marco, and test collections like that. And another one is that at the moment we use cosine similarity to measure the similarity between different passages. Other approaches like entity relationship, word embeddings like word to vector, BERT, or different LDA approaches like topic modeling can be used in the future as well. So this is something that we are looking forward to do in future. So yeah, that's about it. Are there any questions? Thank you very much.